Hello everyone, I'm Juntao Wang. I'm very glad to introduce our work, Cursed Yet Certified Agent. This is a joint work with Alon and Yiling Chen. In this work, we explore the auction design for agents who suffer the winner's curse. Let's first consider an auction game called the wallet game. In this game, Alice and Bob put all their money into a wallet. Alice has X and Bob has Y. They all know the amount of their own pocket money, but not the others. But they all know that X and Y are independently uniformly distributed between 0 and 100. Now the wallet is auctioned back to them using a second price auction. Suppose you're Bob and you know you have $30 put into the wallet. How would you bid? Intuitively, as the expectation of Alice's money is $50, so this wallet is worth $80 to Bob in expectation. And as it is a second price auction, truthful bidding is optimal, so it's very natural for Bob to bid 80. But here is a problem of using this strategy. Bob's strategy is actually bidding his own money Y plus $50. Suppose Alice adopts the same reasoning as Bob, she should also bid her own money X plus 50. So in this case, Bob only wins when his own amount of money is greater than Alice. So conditional case of Bob wins, Alice's money is no more than 30, and the expected value of the wallet that Bob can win is only 45, instead of 80 as what Bob expects. On the other hand, as Alice's strategy is also bidding X plus 50, so the expected payment of Bob when he wins reaches 65. So it turns out that Bob loses $20 in expectation if he wins. This phenomenon is called the winner's curse. It happens in interdependent valuation auction, where the item's value is jointly determined by each agent's private signal. And the winner often behaviorally overestimates the value of the item and pays more than it worth. The winner's curse has been consistently observed in many real-world interdependent auctions, such as auctioning the oil drilling rights or book publication rights of baseball players. There are more examples of it in the book by Kagel and Levine. Sometimes the results of the winner's curse are serious. It may lead to bankruptcy of companies as they may overpay what it get from the auctioned item, making them unable to provide service to the public. Evidence also shows that when a company learns that it could not have accurate information about the item and may overbid, thus suffering the winner curse, the company may be less likely to join future auctions. An example is companies that do not allocate in the neighborhood of the oil field for auction. Also, Aston and Robin have also established classical theories to model the behavior of bidders that may suffer winner's curse. So in this work, we studied the problem of designing good mechanisms to remove the negative effects of the winner's curse. In particular, we do not want the winner to lose money. We do not want them to get negative utility and bankrupt, or are not willing to participate in future auctions. And we provide a positive answer to this question. We can design such mechanisms, but as a consequence, the auctioneer may have to compensate the bidders. Compensation may not be good for auctioneer, so we further study in which cases the auctioneer can achieve good social welfare and revenue. In this talk, we will focus on the social welfare part, where our paper also presents the results about the revenue part. In the following, we will introduce our auction setting first, then the behavior model we use for the cursed agent, and finally, the mechanism design problem. For the auction setting, we consider a single item symmetric auction setting. There is a set of n agents, each with a private signal Si, like the amount of money each player has in the wallet game. And there's a public non-symmetric distribution about the signals. And the valuation of the item is jointly determined by all the signals. For example, it could be the sum of your own signal plus a rescaled sum of other signal. We also assume that this valuation function is symmetric for all agents, and it increases in all signals. We also focus on direct auction mechanisms. Each agent in these mechanisms, each agent I submits a BI to represent its signal Si, and the mechanism mechanism consists of an allocation rule denoted by X and a payment rule denoted by PI. Consequently, the utility of an agent I is given by the valuation it gets from the item minus its payment. We also use sigma to denote the bidding strategy, which specifies the probability density of reporting a certain bid given a certain signal. To simplify the notation in slides, when the context is clear, we will drop the notation S minus I. So here are two examples. So when you find something is missing, just remember it is for some given signals of all other agents. Now we're going to introduce our behavioral model for cursed agent. Let's recall the word again. Bob thinks that the value of the item is always 80 given his signal 30. He ignores that when the others bids less than him so that he wins, the other signal is also less than him, leading to a lower valuation of the wallet than he expects. But given 80 as the true valuation of the item, then Bob bids truthfully and rationally. In other words, Bob can do equilibrium reasoning correctly, while the issue is when he considers his utility, he neglects the contingency between other agents' actions and their signals. This is the philosophy of Aston and Robin's model to capture the winner's curse. More formally, here is the expected utility of agent I given the bids of all bidders and the agent I's own private signal under certain bidding strategy. A fully rational agent will compute this joint distribution of other bids and signals using Bayesian rule correctly, while fully cursed agent will compute this joint distribution of other signals and bids as independent conditional on its own signals. So she ignores the contingency between these two sets of variables. Moreover, there's a partial cursed agent called he cursed agent. She estimates this joint probability as a linear combination of both the correct estimation and the cursed estimation with a mixing coefficient he. So we can write out the expected utility based on this wrongly perceived joint probability denoted by EU he. And in the model, cursed agents play the equilibrium strategy with based on this wrongly perceived expected utility function EU he. This model has an elegant observation. The he cursed expected utility can be equivalently written out by this correct joint probability of other signals and bid, but with a wrongly perceived valuation function via he here. This wrongly perceived valuation function is also a linear combination of the correct valuation and the expected valuation given an agent's own signal as I. We call this valuation the cursed valuation for agent I. So given this, the behavior of an cursed agent is actually equivalent to the behavior of a fully rational agent, but with a cursed valuation function. This is exactly what Bob does in the wallet game. He wrongly perceives the valuation function of the item, but bids rationally based on this wrongly perceived value. In the wallet game, Aston and Robin did human subjects experiments and showed that a he around 0.6 depicts the bidding behavior best. Now we're going to discuss our mechanism design problem. We want the mechanism to be exposed incentive compatible for cursed agent. That means when the cursed agent carry out the exposed equilibrium reasoning, truthful reporting is the equilibrium strategy. We call it cursed exposed IC property, and we use a letter C to denote the word cursed. Second, we want the mechanism to be exposed individual rational for cursed agent. That also means that when they carry out the exposed equilibrium analysis, the equilibrium gives them non-negative utility based on their own calculation of the utility. But these two properties does not guarantee the agent won't get a true negative utility, as these two properties are based on the cursed reasoning. So we in particular want the winners does not lose money in any circumstance and want to remove these negative effects of the winner's curse. This is the true exposed IR individual rational property, referring to the true valuation of the agents. Now let's focus on the first two properties, the cursed exposed IC and IR properties. We can reason out following the traditional definitions, but with a cursed utility instead of the correct utility function. By the equivalence result we just mentioned, these two properties are the same to their counterparts for the rational agents, but with a cursed valuation function phi he. So for this reason, we can immediately obtain the space of all direct cursed exposed IC IR mechanisms using the Mason lemma. First, the allocation rule can be identified with the monotone allocation rule. And second, the payment rule follows the Mason's payment identity given the allocation rule. This gives the whole space of cursed exposed IC and IR mechanisms. Now we want to move forward to add the condition to make winner does not lose money, so which is the true exposed IR condition. However, it turns out that adding this constraint makes a mixing of the cursed valuation and the true valuation in the whole system, and is super challenging to analysis. Therefore, in order to get some analyzable insights for option design with cursed agent, we turn to the deterministic option setting. In deterministic mechanisms, the monotone allocation rule becomes the threshold allocation rule. For example, for the two-player case, the allocation rule for agent 1 is to first draw a threshold function based on the signal of agent 2, as this red curve shows. And if agent 1 signal is greater than the threshold given signal 2, then you just allocate the item to agent 1. And we call this threshold for agent 1 the critical bid for her. Then the payment for the agent is just the cursed valuation of the item at its critical bid, plus the initial payment at the zero signal of that agent. Note that in these equations, we have dropped the drop S minus I for the valuation function and the payment function. Then we can add back the winner's no-lose constraints, the exposed IR true exposed IR constraints. Now let's see what the new mechanism looks like. If agent I lose, it gets 0 and pays PI0, which is smaller than 0, so it already satisfies the true exposed IR condition and the agent won't lose money. On the other hand, if agent I wins, then it will get PI and pays PI he at the critical bid of the agent plus PI0. So if this PI is greater than this cursed valuation at the critical bid of the agent, then we're good. The winner still has positive utility. However, if the true valuation is at this point, which is smaller than the cursed valuation at the critical bid, then we need to adjust this initial payment to be smaller than 0 in order to compensate the bidder, so that it will not have a negative utility. So we have this inequality here. And this inequality should not only hold for a certain SI, but for all the signal of the agents that fall in this range. So as this valuation function phi is increasing, so in the worst case, what we need to compensate is the gap between the true valuation and the cursed valuation at the critical bid of the agent, so which is this inequality. Combine both cases together, we now get a relatively simple new constraint to make the cursed exposed IC and IR mechanism also to be a true exposed IR, so that no bidder will lose money even when they are cursed. Now we have derived our first result about what a deterministic cursed exposed IC and IR mechanism look like, where the winner also never loses money. Compared to the classic case, it just has one more constraint on the initial payment of the agent. But now we also know that this constraint means that if the allocation rule is not properly chosen, the seller may need to compensate the bidders. and the compensation is made through the initial payment term. So which means that even the bidder loses, we still need to compensate it. So a natural question is to ask how bad the compensation can be, and can we do a good balance of between compensation and other aspects of the mechanism. Now let's see the compensation term. If you do not allocate, then you introduce no curse and you can just set initial term as 0. However, if you allocate, then you may get this term negative, leading to our compensation. So this shows a natural tension between the social welfare and the compensation. For example, if you want to achieve full efficiency, then you need to always allocate the item to the bidder with the highest signal. So the critical bid of an agent is always the highest signal among others. Using this feature, we can easily construct a natural valuation function like this, and a distribution of the signals like this, such that the compensation increases superlinearly asymptotically with respect to the number of agents, and the social welfare actually only increases linearly. So which results into a revenue loss increases superlinearly with respect to the number of agents. So that's really not a good thing for the auctioneer. So we consider problem of social welfare maximization under the budget constraint of the auctioneer. In particular, we want to achieve the exposed budget balance, which means that the auctioneer never loses money. It is said that for any bidding profile, the sum of the payments is always non-negative. This again tends to be a very challenging condition to incorporate into the mechanism design problem directly, but we have a subtle way to address this. We first consider seemingly stronger but simpler property, which is the no positive transfer constraint, which means that the seller never compensates to the bidders. In other words, the payments are always non-negative for all agents. Well, we show that if the valuation function and the signal distribution satisfy the Curse monotonicity, then these two constraints are equivalent. And this monotonicity generally means that if other signals decrease and your own signals increases, then you are more likely to overestimate the value of the item and thus suffering the winner's curse. So this is very natural property. And the classic valuation function, such as linear function and concave sum function with independent signals, all the valuation function, the marks of the signals all satisfy this monotonicity condition. So this property is the main building block of our theory about the social welfare maximization, and one of the technical challenges we have attacked. So the proof of the proposition uses the contradiction. Suppose there exists such case that the compensation is needed, then we can iteratively show that if we reduce one more agent signal to 0, then the agent also requests compensation by using the monotonicity and the symmetry of the signals. In the end, we reach to a stage where there's only one positive signal and all other signals 0, but we still need to compensate all other agents. In that case, if we sum up the payments, then we'll find that it will violate the exposed budget balance condition. So equipped with the previous proposition, so we could reduce the problem of designing an exposed budget balance mechanism into designing a no positive transform mechanisms. And to get such mechanisms, we propose the masking operations. That is, given any threshold T, if it induces a winner's curse, thus a compensation is needed, then we just increase the threshold into a point where there's no curse and compensation needed. So this figure shows just one type of relationship between the true valuation and the cursed valuation. So there could be others. So this point may not exist. In that case, we will raise the threshold to the maximal possible value of the signal so that no allocation will be made given fixing signal profile of the other agents. We show that if we apply this masking operation on the generalized figure allocation rule, then we get the optimal social welfare with the exposed budget balance constraints and the cursed exposed ICL constraints, and the winner does not lose money when he wins. This theory actually gave a very interesting observation. If the valuation function of the agent is the max of all signals, then the winner is always cursed, and the optimal social welfare, where no winner loses money and no compensation is made, has to be 0. So we are wondering, is there a case that the auctioneer can make good social welfare with exposed budget balance constraints? And the answer is yes. If the valuation function is a concave sum function and the signals are independent, we can achieve half of the full efficiency when the number of the bidders is large. And the concave sum functions are just a concave function of the sum of any increasing functions of signals. So it covers a wide range of functions such as linear functions and LP known functions. For all these functions, we're good to get half of the full efficiency without compensation. Coming back to our wallet game, this optimal social welfare optimal auction is to allocate the item to the bidder with higher bid when the other bidder's bid also exceeds $50. And the high-level intuition is that to achieve the balance of compensation and social welfare, we have to allocate only when the majority of bidders are the high-end bidders. So these are our results about social welfare. We also provide the revenue optimal mechanism for cursed agents and show that both the optimal revenue and the optimal social welfare decreases with when bidders are more cursed than not. So although we explore the mechanism design problem for cursed agent, and we focus on the deterministic and symmetric setting, it will be very interesting to extend our setting to more general settings such as randomized mechanisms and asymmetric settings. Another interesting problem is that what happens if agents have heterogeneous curse parameter key, and what if the auctioneer cannot know the exact key, and can we design prior-free mechanisms? A more promising direction is to relax the exposed IC constraint to the interim IC constraint. This is because exposed IC constraint requires the allocation rule to be monotone, and you have to allocate to agents with the highest signals. If you focus on interim incentive compatible constraint, then the allocation rule needs not to be monotone, and you will have a larger space to select the winner, and you may not need to compensate. For this direction, Bridgman et al. Provided a very interesting revenue maximization work when the valuation function is the maximal of the signal of agents. That's all about our talk, and thanks for your listening.